Momentum, by definition, is the product of mass and velocity of an object. This definition leads us really nicely into the equation. Momentum, P, equals mv. So kind of weird notation here, right? Momentum does not start with a P, but we use P to represent momentum. Kind of, we already use M for mass. Capital M is an abbreviation for mega in the SI system. So we needed something different, so we went to a Latin, kind of the Latin term, old Latin term for momentum started with a P, so that's what we use for it. M is, of course, mass, V, velocity. So momentum equals mass times velocity. Unit-wise, because we're taking mass times velocity, that's kilograms for mass, meters per second for velocity. And it turns out that is, on its own, the unit for momentum. There's no special unit like newtons or joules or anything. It's just the two things together, kilogram meters per second. So anytime we're talking about momentum, you could say it has 10 kilogram meters per second of momentum. With momentum, we can kind of revisit Newton's second law a little bit. Right. Newton's second law in a very simple form said that force was equal to mass times acceleration, or net force was equal to mass times acceleration. And we have kind of a different way of writing it now that we have momentum. We could also say that force is equal to a change in momentum over time. And it turns out that those two things are equivalent. So let's take a look at that real quick. So momentum, right, is mass times velocity. So change in mass times velocity over time is another way we could write that, right? Change in mv would be change in momentum. Well, in most cases, mass is not going to change. It's going to be the same object, so the same mass. So we can sort of factor that out by saying that mass isn't going to change. It's the changing velocity that's going to change momentum. So mass times change in velocity over time. Well, a change in velocity over time, right, maybe we write it this way and it looks more obvious. Well, a change in velocity in time is an acceleration. So mass times acceleration. So the two things are equivalent. And actually, the top form that we have here with momentum, change in momentum over time, is the original way that Newton actually wrote his second law, because he did it with calculus, and this symbol change in actually has kind of a special meaning there. So this was the way he actually wrote his original second law. So the two things are equivalent. When we say it's a Newton second law problem, you can use either form, ma or change in momentum over time. Depending on what you're given, one way might be easier than the other. Impulse is something that's very important when it comes to momentum, and especially in analyzing collisions. If we have our new form of Newton's second law, delta P over T, we're going to rearrange that and say that change in momentum equals force times time. This part of the equation here, force times time, is what we call impulse. And it has a fairly special significance when we talk about collisions, right? The greater the impulse, the greater this part of my equation, the greater my change in momentum. If we're talking about analyzing collisions, this form of the equation is very important. If you think about a car crash, let's say we're going 30 miles an hour and then we crash and come to a stop. So my change in momentum is going to involve that 30 miles an hour to stop no matter how the collision occurs. In a car crash, you probably want to minimize the forces on the person involved. So you want force to be as low as possible for that same change in momentum, because this side can't change. We're still going from 30 to 0. But when we have our force, if I can change this time over which the impact occurs, so increase the time for that change in momentum to happen, then I'm going to decrease the force in order to get the same change in momentum over here. And that's kind of how a car crash is going to work, is that I want to increase this so that I experience as little force as possible. And there's a ton of applications for that idea, that by changing forces and times, you can change the experience of that collision and change what happens in that collision. So a ton of practical examples there. When we talk about our collisions and we're using Ft equals delta P, it's really important that we take a look at this force component and think about what it really means. If we look at a graph of the forces actually involved in a collision, it looks something like this. where as that impact starts to occur, our force is going to increase and increase and increase until you get to sort of a peak force, and then it's going to slowly decrease as those things, kind of slow down, which makes sense in a collision, right? Across that initial impact, as soon as they're starting to touch, the force isn't quite as much, but when they're really together at their maximum point, there's going to be a lot of force there, and then they're going to kind of back off each other as they slow down. So it makes a lot of sense for us, but that doesn't fit well with this equation. There's not just one number for force here that we can put in. So what we're actually putting into this equation is the average force experienced during a collision. The average force, or effective force, as it says on this graph, is sort of this line right down the middle. Because if you take a graph like this and you cut it down the middle, the area under the graph, which is something very important and tells us about this change in momentum, is sort of equivalent if I just do this whole box here. So the area under this curve is equal to the area of this box, and this box is taken by looking at the effective force or average force of the collision. So really, instead of force times time equals average momentum, we could think of this as saying average force times time equals our change in momentum. So in real life, the situation's a little bit more complicated, but it turns out that by just taking the average here, we actually get the real representation of what's happening, which makes this a fairly powerful equation in that even with this assumption, it's still representing what we want it to represent.